This conference will now be recorded.
Hello, everybody. Jordan Girth here with the National Weather Service Office of Observations. Thank you so much for joining us for the Satellite Book Club Seminar Series. This is session number 215. I'm pleased today for the presentation, Limb Adjusting Tropics to a Common View Angle for Nowcasting and Climate Applications, welcoming Dr. Mitch Goldberg from the City College of New York, previously NESDIS's chief scientist. Following Mitch's presentation, our facilitator today is Joseph Patton, faculty research assistant from CSS in College Park, Maryland. As you just heard, this session is being recorded. We ask that you mute your microphone and turn off your webcam unless you are asking a question or, of course, presenting. The Q&A will occur after the presentation, and we encourage attendees to post their questions in the chat, and we will field them in the order they are asked. Of course, if you would like to ask a question out loud, perhaps it's longer than you want to type out, just note that, and of course, we can handle it that way as well. And if you haven't signed in using your full name, perhaps you're using an office account, please note your name when asking a question in the chat. That'll help us follow up. We're always looking for future presenters. Please contact the Tower S team if you are interested in presenting. Thanks to Emily for posting a link in the chat to where you can do that. If you are looking for training materials, Ross Van Til, as you covered there. I'd like to thank the Office of the Chief Learning Officer, the GEO and LEO programs, our presenter, facilitator, all of you for being with us today. Special thanks to Emily and Kashad, who work behind the scenes each and every week to get this off the ground. All right, let's dive right into it today. Dr. Mitchell Goldberg has extensive experience in the development and improvement of algorithms for deriving atmospheric temperature and moisture profiles and trace gases from satellite observations. He has over 35 years of satellite algorithm development experience. After 35 years at NOAA, he retired and became the Distinguished Research Scientist for the NOAA CESRIS program at the City College of New York. CESRIS is a NOAA-funded cooperative science center with the focus on recruiting students to work on research related to NOAA's mission. At CCNY, Dr. Goldberg leads the Satellite Remote Sensing and Applications Lab, where he and his team conduct research in the CalVal and application of infrared microwave soundings from new satellite missions, including new satellite missions related to atmospheric composition and greenhouse gases. Mitch, welcome to the Satellite Book Club, and this is your first time, believe it or not, with us today.
That's right. Thank you, Jordan, and appreciate being invited to give this presentation. And it's been a very interesting transition from NESDIS to City College of New York. I'm still doing a lot of things related to NOAA's priorities and working with students. So, and having this team of researchers that I've been working with. So it was funny how I got involved in tropics about probably 6-7 years ago. I was representing NESDIS at a tropics workshop. So so I would give presentations on why tropics would be important to NOAA, things like that. I also told them that, hey, remember, this is a cross-track scanner, and the data has to be limb adjusted for it to be used for imagery. So I kept on reminding them that. And then last November, about a year ago, they've released tropics data for the very first time. And I said, hey, let me, back in the research game. So I said, let me start studying this data. And I presented some results right away, like the following month, to the tropics science team. And they started to use these limb adjustment coefficients. Now, at the same time, not at the same time, just a few months ago, I'm sorry, NESDIS has this commercial data program, CDP. And for years, they've been buying commercial data related to radio occultation. And that's been successful. It started with a pilot study that basically said that, is this data, of good quality? Will it be impactful to NOAA's mission? And the answer was yes. And that took a number of years. Right now, they've started this new program, new aspect of the program, purchasing microwave CubeSat data um, from a couple of companies. The first one is Tomorrow.io, which I'll show in a chart, that are basically flying something similar to Tropics. And so I'm part of the evaluation team along with Star and others to independently evaluate their CubeSats, which again is similar to Tropics. We definitely want feedback from Weather Service on applications, both in data simulation as well as also using the data in real time. So I'll talk more about what these CubeSats are and what they mean. You know, it could be transformational for NESDIS. So if we go to the next slide, please. And Bill Blackwell is the PI from NASA. So I should say that TROPICS is a NASA-funded project demonstrating CubeSats. You know, these very small, affordable systems that will basically give you better temporal refresh. And so I'll talk more about that later. Now, this is a slide I generated a long time ago. It was with Weather Service. It's the talking. It focused on the operational use of microwave imagery and soundings. It was a lot of it was focused on imagery because at that time we were trying to get Japan, JAXA, to continue to fly AMSR imagers. And they have not. They at that point they were still on the fence if they wanted to continue to invest in follow-on to AMSR. So we emphasize the importance of why we need microwave imagery and sounders. So this is just a list. So I want to basically draw your attention to this slide that basically shows the different usages of microwave imagery and soundings, from tropical, looking at imagery, to depending on the frequency, you can have all sky SST and winds, and of course precipitation. Of course, sounder channels. Sounders are used in NWP. You can monitor ice, and some bands you can actually look at soil moisture. So let's go to the next slide. Yeah, so this was like a screenshot we gave about microwave imagery, and people like microwave imagery because it's very sensitive to precipitation. It can see through clouds. You can easily find, you know, the eye of a tropical system um, versus infrared. When it could be obscured. So people like it, right? It's very useful. The thing that we don't like is that temporal sampling is not so good. And this was an example showing that AMSR2 definitely helps with the temporal sampling. So you would have like 3Z from AMSR2, then these are the SSMIs, 6 and 8, and then back to 16. And that's definitely important, but it's still the temporal sampling is not still insufficient. So if, please, let's go to the next slide. And so now we have these little instruments. They're miniaturized using new technology. And so that's like a depiction of JPSS versus TROPICS. And that TROPICS is actually enlarged by 50x. There's this new channel that we never had before, the 205 gigahertz channel, that is very, very sensitive to ice particles and very useful for estimating precipitation. So that's actually the channel you want to use, the 205. I think the next generation of JPSS will probably have the 205. The Europeans, the next generation of EUMETSAT that will be launched, I guess, later, I guess next year sometime, we'll have the 205. So that's a really good channel, and Tropics has that. And so this is a comparison, for example, of for two tropical storms. One is a typhoon, the other one's a Hurricane Ian, and so forth. And so from JPSS, you can see the 183 gigahertz, and then you see the 205. And you can just see the features are sharper just because they both have about the same spatial resolution. It's just the different frequency. So that's good. Let's go to the next slide. And so, of course, what you can detect from microwaves is a function of the frequency. So this is an old chart from JAXA that basically says, which channels you have to use. So AMSR, for example, provides all these channels. So you can do a lot. Sea ice, soil moisture, wind speed, etc. So you can do a lot from AMSR. And then the next slide should be just bands that one would use for atmospheric soundings. This is from ATMS, and so so that's from ATMS. Now, Tropics actually uses the 118 gigahertz area, the one to the right in the middle of those green columns, and those channels are more affected by cloud-looking water. However, we're able to get better spatial resolution by working the 118 and the optics. Everything is smaller, so we can actually they can actually put it in a small CubeSat. So now we're working with the 118, which is okay. That's something that we have to learn more about and sort of quantify and evaluate the data as well. Next slide. So this is a list of tropics channels that we have. Again, channel 12 is important. Notice the nadir footprint is about 15 kilometers, which is pretty good. And 9 through 12 are basically the water vapor channels. 2 through 8 are the temperature sensitive channels, and of course then you have the 90 gigahertz channel that is sensitive to clouds and precipitation as well. But those channels 1, 2, 3 are very sensitive to the surface, and so sometimes you get mixed signatures when trying to analyze a tropical system. You rather use the atmospheric water vapor channels, which are basically 9 through 12. Okay, next. Let's see, next slide, please. Okay, and so this is from Bill Blackwell, basically shows the journey of these first CubeSats. If you go back one slide. Back, please. Yeah, next. Okay, stay on this slide. So CubeSats, it's only first one deployed 2018, right? So it's like someone inventing cell phones back in the 1990s or 1980s. Like, right back in the day, one would say, I'm never going to get rid of my landline. What are you, crazy? And now we can get rid of our landline. But we're far from that, So, there's two companies. OMS is one company, the other one, commercial. I am jumping ahead, but this is the timeline. And now Tomorrow.io is launching a constellation. Launched two of them already a couple of months ago. And they're planning that one's in a regular polar orbit, sun-sync orbit, and they're planning on launching two more in the next few months that will be low inclination, sort of like tropics today, which I'll show you more soon. And then there's this other commercial company. They deployed something in 2019, OMS. Both companies actually have contracts now with the NESDIS commercial data program. And again, like I said earlier, I'm part of the team that will look closely at these measurements and characterize them as best as we can. Next slide. Okay, and this basically shows the tropics. What's up there now? There's 3 satellites that are active. 03, 05, and 06. And basically shows the orbit. This is the low inclination activity. Now we're stuck with like, they basically try to get launch rides, right? Things that going to go into space, and so they just piggyback on these systems. And so, for example, S5 and I think it's S5. Let me see, S5 and S3 are on the same, basically in the same plane, even though you wouldn't want that. But that's the only ride they could go. Tell me if I saw a little signature. I saw a message on my computer saying poor network connection. So if you have any
We're
problems,
good.
I'm good. Okay, good. All right. So all right. So next slide basically shows a nice. I think. Yeah. Go to the next slide, please. Oh, this basically shows the weighting functions. So on the left are basically the temperature channels. On the right are the water vapor channels. Uh, Pretty good, and the temperature channels are not so, it's not as good as ATMS for sure. But the water vapor channels are pretty good, and so we have good water vapor coverage from tropics. Okay, next slide. Now, okay, okay, and so in the limb adjusted, if you click on the lower left, it's a little movie. Um, And basically, the weighting functions as you look further away from nadir, because this is cross track, and you can play it again. Um, the weighting functions lift; they become higher in the atmosphere, and that's due because the optical path is higher, so you have more absorption. Um, that has to be corrected. Unlike AMSR, like AMSR and SSMIS, they're conical scanners, so it's always at the same viewing geometry, so you don't have to worry about that. But that has to be corrected, and so we have a technique in doing that. So next slide, please. Next slide. Okay. So picture's worth 1,000 words, right? So this is channel 9, upper tropospheric water vapor. A lot of people like to use this for atmospheric rivers. And so this is if you don't do anything to the data and just plot it, you have the limb effect. This is after you do the correction at the bottom, everything looks good. All right. So the limb adjustment is critical. Next slide. Okay, so wide limb adjust imageries, water vapor imageries used routinely by weather forecasters. We know that. We look at atmospheric rivers, things like that. Microwave water vapor channels have the advantage of less cloud contamination, but the temporal refresh is rather poor, which I already mentioned that. But now we have potentially the constellation of very affordable cubesats that would give you the higher temporal refresh, so that's a good thing. The limit effect I already talked about has to be corrected. Also, if suddenly you have a constellation of 18 of them, you really have to account for differences between instruments. I don't have time to talk about all that, but trust me that there are differences between instruments, and you have to account for them. And suddenly, if you had 18 of them, you just have to come up with new techniques of mitigating these artifacts. And limb adjustment is one way for nowcasting applications. It's very quick, very easy to do that. Okay, next slide. Okay, so this is geostationary. Everyone loves geostationary, right? But there's clouds and things like that. Let's go to the next slide. The next slide is channel 9 upper tropospheric water vapor channels. I'm trying to compare the left with the right. And so you can see after the limb adjustment, you get this enhancement of the signature because you're getting rid of this false signature due to looking higher in the atmosphere because the weighting functions are getting higher. So at the bottom is what you get after you adjust it. And you can compare that with to the right, and you can see it lines up very, very nicely. You get the signature, let's say, east of Cuba. You can see that little wormy, signature that looks like a little worm. And you can see that in the infrared signature. So the limb adjustment is sort of getting the details out. It's really pulling the details, which is nice. Okay, so I'm confident the limb adjustment works. So next slide. Um, and again, we already provided the limb adjustment to the TROPICS science team, and they've been using it and potentially working with folks in Weather Service demonstrating this data. Okay, this should be a movie too. So this is, yeah, click on that. It's just day by day animation. This is what we're striving for. This should be an hour by hour animation, or a at least yeah, an hour by hour type of animation. If one had a really large constellation of tropics like cubesats, spaced equally. Spacing equally is hard because they go for they piggyback on launches that have a you know, a specific you know you know location, launch time, and so forth. So hopefully in the future, getting these small instruments into space will be more affordable, and then you can actually launch them in a equally spaced constellation. So hopefully that will happen too in the future. Okay, so next slide. Um, okay, next. Okay, and now this looks like the data from 3 satellites, even though two of them are on the same orbital plane. Uh, you can tell the two by one of the tracks is a little bit wider than the other one, and that's because they're basically sitting on top of each other, but not exactly. But if you, it's a little choppy when I see this. But if it's not choppy on your screen, maybe it's just the internet connection is not as good here. But if you look at the upper right, um, you know, Northern Pacific, you should see this nice swirl of the storm, so you can actually see this storm soaring. Hey, Jordan, can you hear me okay?
Yeah, we can, and the animation is a little choppy, but we can see the swirl in the North Pacific
Okay.
every once
Yeah.
in a while.
Yeah, so what I'm saying, that's really nice to have. And just again, if we had a whole constellation of these things, it will be a lot better. Right? You're going to be able to a whole constellation. You're going to be able to observe every 30 minutes, and so that will be good. At the bottom is basically the composite for the day. So this is what a day coverage looks like. But this is different from JPSS, right? Because a composite for JPSS would all be at the same local time. This is all different times during the day. So let's go to the next slide. Next slide, please. Okay. And this just shows the different times during the day. So this composite, you can see at the bottom, you can see things from hour 20 versus hour 10. So 10 hours apart in this composite. Okay. So you just have to take that into account. Okay, next slide. Um, Okay, so the technique is clear. It's based on papers I did a long, long time ago. We're basically fitting non-nadir weighting functions to look like nadir. So we use rate of transfer to do that. Next slide. And we have certain constraints that the coefficients have to add up to 1. And this is sort of the fit. So this is like uh, having one of the furthest scan angles, fitting it to nadir. And so on the left, you can see they actually fit pretty well. But that's assuming the instrument is perfect. And so on the right, we have an extra step that basically takes the coefficients derived from the physical model and then apply it to real data, and we adjust those coefficients using the coefficients based on the physical model as a constraint for the final set of coefficients that take into account the real data. So let's go to the next slide. And this is an example of channel 6, which has a really large limb effect. And this is the original, and this is an atmospheric temperature channel that probably peaks in the upper troposphere. And so this is what the original looks like. with the limb adjusted. And so the limb adjustment, you can see again features just like I showed before with for the water vapor channel, but this is a temperature channel. And so over Africa, you can see like precipitation cells and things like that. So it looks good. Okay, next slide. And of course, the reason we do it is because if you want to average the data, let's say over a month, you simply would get nonsense, because you're just averaging stuff from all different angles. At the bottom is after you average a month and you get meteorological features. So limb adjustment is good, not just for nowcasting, but also if you wanted to monitor changes in the climate and actually monitor it. Once you have a constellation, you can look at the diurnal cycle and look at changes of the diurnal cycle too. Okay, next. All right, and this is just a plot that shows the diurnal cycle that we cover everything. Okay, next slide. All right, and this is just a nice picture, 12 channels of tropics for August, just everything limb adjusted. I can actually make a calendar out of it because 12 months, obviously. Okay, next slide. So, we want to quantify these differences. So we want to, not just show pictures. So part of the quantification is important for data assimilation because every 10th of a degree matters in data assimilation. Imagery doesn't matter, right? If you're looking at, systems with large signatures, you're just going to look at the imagery. You don't care about every 10th of a degree. For data assimilation, you need because they're basically really assimilating mostly clear sky conditions. So the top is the channel 11, one of the water vapor channels. And the blue area is basically where there's precipitation. So that's nice. You can actually see beautiful areas of precipitation. The middle is where I actually screened the data for precipitation. A very simple test on the left. And at the bottom is simulation using RT-TOP, which is like CRTM, and using ECMWF. So it actually compares extremely well. This is for a water vapor channel. This is pretty good. And the next slide is, can you go to the next slide? Can you hear me okay, Jordan?
Yep, still good here. You must have just a little bit of a lag.
All right. Okay, next slide. Anyway, I know you can hear me. I'm gonna walk my computer over to the room next door or 2 doors away because I think the signal might be stronger. So
Okay.
sorry about that.
Whatever you need to do, yep, go ahead.
We're still connected, and I hope this will make it better because I still don't see the next slide.
Looks good. We'll see maybe if we can advance the slide back a couple times to see if Mitch's computer can catch up.
Okay, now I see the next slide. Okay, this is now the difference between, oh, you have to go one more back to the next slide. So the next slide will be the difference between channel 11. The top one is observed. The middle one is simulated, and now the difference. Difference doesn't look so bad. Very small differences. So that's pretty good. There are things at the edges that might have to do with the satellite itself. So we're looking at that, but anyway, let's go to the next slide. The next slide should be a sequence of looking at the different channels. So this is now what I'm studying now is the difference between satellites. So this is S6 versus S3 satellites for channel 9, 10, 11, 12. And there are differences, there should be differences because there are differences due to time. So in this image are differences because the satellites are observing a different time. Now there's a paper which I refer to in the next slide, which basically shows there's certain parts of the region where diurnal cycle here, these little areas where the diurnal cycle is very small in terms of water vapor. So if you go back to the previous slide for a second, you'll see in those areas the differences are rather small. Can you go back one? Yeah. So these differences here, I know I'm moving my mouse, you can't see it, but if you see west of South America and east of South America, these are areas where the differences are small, and statistically they are small. They have small diurnal cycle, but we want to do it the right way. And so if you go, we do the double difference. So if you go to the next slide and the next slide after that, and then we're almost done with the presentation. Okay, so the next slide is now simulation minus simulation. So this is everything simulated. So these differences are really differences due to the model at different times. So it's taking account the time difference. So if you think of the first slide, which was actually real data, observed minus observed for the two different satellites, you take that difference, you subtract off this difference, that's the famous double difference, and then you get the next slide. And the next slide will show that. Go to the next one. Yep, and here's a double difference. Looks a lot smaller, especially 9 and 10, where you're not really sensitive to the surface at all. And so these are really small differences, not that bad, but they have to be constantly monitored. Again, ATMS, for example, is rock solid. That thing is so stable. But with ATMS, you launch one, then you launch another one, 5 years later, and they're in the same orbit, so they're not adding much more information. So you have your time to characterize this. Here, with these CubeSats, if you suddenly have 18 of them, and they only last for a couple of years, and they're always being replenished, let's say the model in the future could be that just constant launches and they're just being replenished all the time, you get a lot higher temporal refresh. They're good for monitoring tropical storms. It's great. We don't have to really worry about that too much because the signature is pretty large, and so that's fine. But if you want to look at data simulation, you got to really thoroughly understand the differences between the satellites. And so it's basically, it's very difficult, but it can be done, but it requires a lot more investigation. Okay, so let's go to the next slide. And so let's see, next slide, please. Oh, this is looking at a hurricane, Hurricane Otis. Now, I did notice these are channels which you wouldn't really use anyway, but I did notice that the limb adjustment seems to be washing out the signature. The first one's the original data. The second row is with the limb adjustment. And I think that has to do with having such a large surface component for these channels. But I'm not so worried about that. I have a kludge in order to sort of adjust it, which I show in a couple slides later. But the next slide, for the atmospheric channels, it looks very good. This is the original data and the limb adjusted. Not really much difference, except for like channel 9 has you do want to limb adjust. But in terms of the signature, actually, I think the signature is a little bit sharper. But remember earlier I said channel 12 is the one that you want to use. Channel 12, even without limb adjustment, looks pretty good. But if you're looking at upper tropospheric water and looking at atmospheric rivers, you definitely want to limb adjust. But the limb adjustment works really well for all these water vapor channels, so which is good. Okay, so next slide. This is the little thing we can ignore this, but this is basically don't apply the limb adjustment if there's precipitation for channels 1 through 4. So anyway, but let's not worry about that. Okay, next slide. So next slide should be a conclusion or summary. Yep, so these are the requirements for CubeSats and NWP. You need to account for biases between instruments. We need to do fast characterization of the different sensors. We have to make sure we have pre-launch characterization a lot of times, and healthy pre-launch characterization. a lot of times we know what the differences are going to look like in ATMS before we even launch ATMS because of the pre-launch data. So that's really important. Using rate of transfer to understand differences, double differencing, which I showed an example of that. Using limb adjustment allows for quick analysis of the stability, and also reanalysis, based on high quality benchmark observations to bias monitor. We sort of do that now, but also using ATMS as a benchmark. ATMS again is rock solid, and we've been doing different techniques of demonstrating to ATM. Anyway, I've been noticing for some of the tropics data, it seems like there's some instability, especially for the temperature channels that I've been detecting, and that definitely has to be screened in. And ATMS can be used as an anchor because there's no such instability with ATMS. And so we're going to try to show, come up with, quantitative tools to continuously monitor the stability of CubeSats, but always use ATMS as a reference because we know what it should really look like if something was of ATMS quality. So having ATMS as a benchmark is really important because it shows ideally what to expect. Okay, next slide. So things to do. So once we get the commercial data coming in, we're going to generate the limb adjustment coefficients for real-time imagery applications. We love to have feedback from weather service using the test bed, like the severe weather test bed. I sort of said this already about continuously characterizing the performance of the CubeSats, so I don't have to repeat it. And next slide is so summary. The tropics data looks good. The water vapor channels look good. We expect the data from Tomorrow.io, for example, and OMS to hopefully look as good or potentially better. Limb adjustment allows easy interpretive imagery applications. So that's very important, and getting feedback from the forecasters is really important. So I'm sure the commercial data program will want to work with Weather Service on this. We're going to do more comparisons, deep dive analysis of the quality of the data. We're also looking at doing retrievals as well. Again, this is not replacing ATMS. This is more enhancing ATMS. ATMS and the European microwave sounders, they're backbone anchors, they're backbone systems. High performance, long lasting, very, very stable. But the downside is the temporal refresh. So if we can have a swarm of CubeSats providing us with a temporal refresh anchored to these backbones, I think it's going to have significant impact to NWP applications. Thank you very much.
Okay, thank you, Mitch, for that presentation. It was really interesting to hear all that information about this CubeSat system and how that processing works. I want to encourage attendees to please stay on for our discussion period. Especially, we want to encourage participation from the field forecast offices and regional headquarters. And we also encourage everyone to change your view setting to active cameras from the default view. So if you click that button in the top center and then click the option for active cameras, you'll see me and the speaker, Mitch, as we go through this discussion section. So I also want to remind attendees to submit questions in the chat, or they can indicate in the chat if they want to ask a question verbally. So we'll dive right in. Emily is now posting the link to the Satellite Book Club feedback form during this discussion section. So please share any feedback you have on this session or the Satellite Book Club in general in that short survey in the chat. I want to mention before we get to the questions, a week from today, on Thursday, November 21st at 12 p.m. Eastern Time, Heather Kenyon, a meteorologist from the National Weather Service Forecast Office in Buffalo, New York, will discuss an operational forecast perspective of the historic Buffalo, New York blizzard of December 2022. So that was a very impactful blizzard, a great exercise to get into our winter weather here. Please contact the TORS team if consisting of Kashad Bowman and Emily Maddox for questions about the Satellite Book Club or for configuration of any satellite products in your workstations. So now let's begin the discussion. Again, you can submit your questions to the chat. But to start off, I have a couple questions that we can start out as a discussion point. So you had mentioned that we are getting into this phase where we have these commercial CubeSat microwave sounder constellations like the one from Tomorrow IO. And I'm wondering what you envision as far as how that impacts the private enterprise data is going to have on public and academic institutions. Do you expect National Weather Service forecasters, for example, to have access to that data in real time?
Sure. The commercial data program at NESDIS, usually when they buy the data, they pay extra. It costs a little bit more, maybe a lot more, but they make sure the data is open and free for everyone, not just for NOAA, but for other institutions as well, for other government agencies. And so that has been done with radio occultation. At first, I think in phase one, it might have been only open to U.S. government, but now, the CDP program, they basically, provide access to all.
Okay, great. That's great to hear.
So you won't have an issue with that.
We have a question in the chat. Thank you for your presentation, Mitch. Are you comparing all sky observed versus clear sky simulated? If so, then where do you account for the cloud impact?
Okay, so all sky, I'm sort of weeding out the cloud by using this test where I filter out. I use that test that basically says only keep data that's warmer than 263 for channel 11. It seems to work fairly well. Now I could have gone a little bit further with that and made it more stringent. Like for example, ECMWF reanalysis does have their own estimate of cloud liquid water, so I can say only use those data where the cloud liquid water is nearly zero, according to ECMWF. And then I could also applied further cloud liquid water tests within the data itself. But I didn't have those algorithms, so I just made it a very simple test. It seems like it works fairly well, though, based on the differences that I've been seeing. But there's probably, probably some contamination still creeping through.
Okay, awesome. And just one more quick question. We are kind of up against our time limit here. We had talked briefly about potentially having some imagery applications fall out of hazardous weather test beds. And I wanted to get your perspective on what those additional applications that we don't have yet might be that you think might be possible from these CubeSats.
Well, I think the imagery applications themselves, and so the current applications that are used today, using microwave imagery, should simply be extended, right, using the CubeSats. So it's not creating something totally different. It's just providing similar products, information, but you have a higher temporal refresh. And so I know the commercial data program at NESDIS is looking towards working with Weather Service to get feedback. So there are Weather Service folks on that team, CDP team, purchasing the Tomorrow IO data and so forth. And the NASA TROPICS science team also, part of it involves the application team is led by sport, in Huntsville, the sport team. And they've been also, I think, seeking feedback from Weather Service. But I think it's probably more ad hoc. But I think that with CDP, they want to formalize that. I was at a meeting and that was discussed about how do we get Weather Service more engaged in providing us feedback. So So we would look really, so it's really important. So my perspective is that it's really important to work with Weather Service and get your feedback and come up with the easiest way of making it really cost effective. And so initially, obviously there's going to be some website available that will provide the data that way, and then and somehow provide the feedback. Uh, you know, and I'm sure there'll be some training involved too. So we'll make it work. I mean, this is something that NESDIS working, the GeoXO program, the JPSS program, so forth, working with Weather Service. They have a strong history of getting the groups together and getting feedback. So I see the same things taking place.
Okay, that's really good to hear. As a former forecaster, that's great to hear. Okay, so we want to go ahead and conclude the discussion now, and I'll pass it back to Jordan for our final remarks.
Thank you so much, Joseph, and thank you, Mitch. I want to apologize. I really stumbled over the name of SSIRST in the introduction. Something about combining it with another cooperative institute got me tongue-tied. Anyway, great presentation. Thank you for all your work on tropics, and I know our field offices are very excited, particularly our national centers as well, about the tropics data and how that could improve our marine and tropical service areas. So with that, as Joseph has already pointed out, the Satellite Book Club continues a week from today. So you can join us next week to learn about the historic Buffalo, New York blizzard of December 2022. If you need to reach out to the Satellite Book Club, you can, of course, get in touch with Kashad and Emily via email or over the Slack channel at any time. One last note today, while the Satellite Book Club will continue next week, my time as a host has largely come to an end as I am moving on to a new position with NESDIS Systems Architecture and Engineering starting on Monday. Thank you so much for allowing me to bring you this Satellite Book Club content over the past 4 years, and certainly hope that the book club is able to continue, and I will certainly join intermittently and maybe even guest host then and again. So with that, I'd like to thank Mitch once again, Joseph, Kashad, Emily, everybody behind the book club, and all of you for being with us today. Thank you so much. Take care and join us again for the book club next week. Bye now.